The universe is not a quiet museum, but a theater of constant and violent transformation. We will uncover 25 specific cosmic events with the power to reshape everything you know about reality. By the end of this journey, you will possess a new perspective on time, space, and our own fragile existence. We will see how the silent drift of entire galaxies and the explosive death of stars could one day rewrite the cosmic rulebook. What mysterious force could tear the fabric of space itself, and how might the universe meet its final end? How does it feel to contemplate a cosmos in perpetual, dramatic change? A gentle breeze, a warm summer day, the very light that gives life to our world, all of it is borrowed time. The star we orbit is a temporary benefactor, and its eventual transformation will rewrite the story of our solar system. Billions of years from now, the sun will exhaust the hydrogen fuel burning in its core. This is not an explosion, but a slow and inevitable swelling. It will balloon outward into a red giant, a phase in its life cycle that spells a definitive end for the inner planets. Mercury and Venus will be the first to be engulfed, vanishing into the sun's now vast and tenuous outer layers. Earth will face a more protracted fate. Long before the star's surface reaches our orbit, its increasing brightness will scorch our world. The oceans will not merely evaporate, they will boil away into space, leaving a barren, molten rock behind. The very atoms that once formed our continents and seas, the calcium in our bones and the iron in our blood, were forged in the heart of a long-dead star. In its final act, our sun will reclaim them, scattering this stardust back into the cosmos to be part of new worlds, new stories. This cosmic recycling raises a profound question for our search for life beyond Earth. If even stable, sun-like stars carry this expiration date, then life on any orbiting world may be a fleeting phenomenon, a brilliant but brief candle in the long cosmic night. Our own star's destiny sets the stage for far greater upheavals on a scale that dwarfs single solar systems. But our own solar system's fate is just a single chapter in a much grander story of cosmic change. Two majestic spiral islands of stars, our own Milky Way and the great Andromeda galaxy, are currently falling toward each other in a slow-motion embrace that will last for billions of years. This is not a violent, fiery crash as you might picture, but a stately and graceful dance choreographed by gravity. The two largest members of our local group are inextricably drawn together. Scientists like Dr. Roland van der Merle of the Space Telescope Science Institute have used detailed data from the Hubble Space Telescope to confirm this future merger, noting it will completely transform the night sky from our perspective. As the galaxies first swing past each other, their immense gravitational forces will act like tidal waves, pulling and stretching their beautiful spiral arms into long, streaming tails of stars. They will then swing back, eventually merging into a single, larger elliptical galaxy that astronomers often call Milkdromeda. Throughout this immense process, direct collisions between stars will be incredibly rare because of the vast distances separating them. The real action will happen within the colossal clouds of gas and dust. As these clouds slam together, they will compress, igniting a spectacular firestorm of new star birth. Our own solar system will likely be gravitationally flung into a new orbit within this hybrid galaxy, watching from a distance as the familiar constellations of our night sky are utterly rewritten. What does such a peaceful, billion-year collision tell us? It reveals that galaxies are not static islands but dynamic, evolving entities, constantly interacting and merging to build new structures. This grand galactic future is shaped by the same force that governs the universe's ultimate fate, the mysterious and accelerating expansion of space itself. Yet this grand cosmic dance of galaxies will itself be a temporary spectacle. The same force that brings them together, gravity, is locked in a long-term struggle with a far more mysterious power, a force that promises an even more profound and chilling conclusion. Picture the universe not with a bang, but with a whisper, a slow, inexorable slide into a state of permanent and profound stillness. This is the heat death of the universe, often called the Big Freeze. It is the ultimate triumph of a principle known as entropy, which, in simple terms, is the universe's natural tendency toward disorder. Over timescales so immense they make the current age of the universe feel like a single heartbeat, all the usable energy in the cosmos will gradually be used up. Stars, from the largest blue giants to the smallest red dwarfs, will one by one exhaust their nuclear fuel and fade to black. The last flickering embers of stellar furnaces will go dark, leaving behind a cosmos populated only by the cold, dead remnants of stars, neutron stars, and white dwarfs, which will themselves cool over eons until they are no warmer than the background temperature of space. Even the mightiest black holes are not eternal in this scenario. Through a subtle quantum process predicted by Stephen Hawking, they will slowly leak radiation and evaporate, vanishing over almost unimaginable spans of time. The universe will be left as a thin, ever-expanding soup of isolated fundamental particles and radiation, all at a uniform, frigid temperature, just a fraction of a degree above absolute zero. In this state, no energy can flow from one place to another, no work can be done, and no form of life or complexity can possibly exist. It is a final, universal equilibrium. The Nobel laureate Steven Weinberg once reflected on this, suggesting that the more we comprehend the universe, the more it can seem devoid of point or purpose, a sentiment that captures the profound emptiness of this potential finale. What meaning can our brief, vibrant lives hold in the face of such an immense and silent eternity? This ultimate quietus, however, is not the only path written in the cosmos. Its inevitability hinges entirely on the behavior of that mysterious force driving the universe apart, the same dark energy that began its work with a far more violent and creative act. The profound stillness of the Big Freeze is not the only possible end. There exists a far more violent and immediate finale, one where the very fabric of reality is shredded by its own accelerating expansion. This is the Big Rip, a hypothetical scenario born from the most sinister form of dark energy. If the mysterious force driving galaxies apart is not constant, but instead grows stronger over time, its influence would eventually become absolute. Cosmologist Robert Caldwell of Dartmouth College, who helped pioneer this idea, paints a chilling picture, describing a future where the expansion becomes so rapid that it literally rips apart all bound structures. The end would not come from outside, but from space itself stretching at an infinite rate. First, the immense gravitational glue holding clusters of galaxies together would be overwhelmed. These vast cities of stars would be flung into the ever-widening emptiness, isolated and alone. Next, the individual galaxies themselves would be dismantled. The spiral arms of the Milky Way would be pulled into streams of stars, each one set adrift. Then, solar systems would be torn from their galactic anchors. The Sun's gravity would be powerless to hold onto its planets. In the final moments, the forces that bind matter itself would fail. Planets, then mountains, then molecules and atoms would be violently pulled apart. Even the nuclei of atoms would be shredded into their constituent quarks, a fraction of a second before the concept of time itself loses all meaning. The timeline for such a cataclysm depends entirely on the true nature of dark energy, a mystery that current telescopes are desperately trying to solve. Could our measurements of distant supernova and galaxy clusters be subtly pointing toward this ultimate disintegration? To grasp how such an extreme fate is even possible, we must first look back to the very beginning, to the moment that set this entire cosmic story in motion. The very laws of physics that hold our reality together might be resting on a foundation of sand. This brings us to a deeply unsettling cosmic possibility: the decay of the Higgs field. Think of the universe not as a solid, permanent structure, but as a ball sitting in a shallow dip on the side of a very steep mountain. This dip is what physicists call a false vacuum, a state that seems stable for now, but is not the lowest possible energy state the universe could achieve. The Higgs field is what pervades all of space and gives fundamental particles their mass. Without it, electrons would whip around at the speed of light and atoms could never form. But what if this field is not in its true, most stable state? The late, great Stephen Hawking highlighted this worry, pointing out that the Higgs potential could become metastable at incredibly high energy levels. If a quantum fluctuation, a random tick in the fabric of reality, were to create a tiny bubble of this true vacuum somewhere in the cosmos, the consequences would be absolute. This bubble would expand at the speed of light, its wall rewriting the laws of physics as it moves. Inside this new region, the properties of the Higgs field would be different. The forces and particles that allow for atoms, molecules, and life itself would cease to function. The universe as we know it would not end with fire or ice, but with a silent, light-speed correction that erases the very rules of chemistry and matter. The good news is that the probability of this happening in any given year is astronomically small, far longer than the current age of the universe. Yet, the mere possibility that the fundamental constants we rely on could be temporary reshapes our understanding of reality. It suggests our cosmos might be a fleeting, precarious arrangement in a much vaster and stranger landscape of physical laws. This threat to the cosmic rulebook from within finds a parallel in the large-scale structures that govern the universe, the fate of the vast cosmic web that connects all galaxies. The same dark energy that threatens to tear apart matter itself is already at work on the grandest stage, methodically dissolving the universe's very architecture. We call this magnificent structure the cosmic web, a vast network of dark matter filaments that connects all galaxies, a tapestry woven by gravity over billions of years. Within this web, brilliant clusters of galaxies gather at the intersections, while immense, empty voids stretch between the glowing strands. This intricate design is the backbone of our cosmos, but it is not permanent. The relentless push of dark energy acts like an invisible solvent, weakening the gravitational bonds that hold this structure together, as cosmologist Mikael G. Ray of the University of Helsinki explains. In an accelerating universe, the cosmic web is freezing out. Future observers will see only their own galaxy and a void of darkness. Picture our local group of galaxies having merged into the single entity of Andromeda, floating in an ever-expanding sea of blackness. One by one, distant galaxy clusters will be pushed beyond our cosmological horizon, their light stretched and reddened until it can no longer reach us. They do not vanish in a flash, but simply fade from view like ships disappearing over a curved ocean. The grand pattern we see mapped by telescopes today, the great walls and filaments, will slowly unravel and vanish from the sky. The universe becomes a collection of isolated islands, each unaware of the other's existence, with the large-scale structure fading from view long before the last stars die. This is not a violent end, but a quiet, profound erasure of context. How do we comprehend a cosmology where the subject of study, the universe itself, steadily retreats from our view? This dissolution of the cosmic web forces us to confront a future of cosmic isolation, a prelude to the final fates awaiting the last stars. At the very heart of our own Milky Way, and nearly every large galaxy we can see, lies a gravitational monster. These are supermassive black holes, cosmic engines with masses ranging from millions to billions of times that of our Sun. Their origins are one of the great puzzles in modern astronomy. How did such behemoths form so quickly in the early universe? One leading theory suggests they grew from smaller seed black holes, the remnants of the first massive stars. Another, more dramatic idea, championed by theoretical astrophysicists like Dr. Priyamvada Natarajan of Yale University, points to direct collapse. In this scenario, giant clouds of pristine gas in the infant cosmos could have collapsed under their own weight, not into a star, but directly into a black hole of immense proportions, skipping the stellar stage entirely. These direct collapse seeds would have been born large, giving them a head start in a cosmic feeding frenzy that allowed them to grow to their staggering sizes. But these black holes are not passive residents. Their influence is profound and far-reaching. As matter spirals into them, forming a superheated accretion disk, it releases unimaginable amounts of energy. This energetic feedback can blast through the galaxy, heating gas and pushing it away, effectively shutting down star formation in the central regions. In this way, a supermassive black hole acts as a cosmic regulator, its violent appetite helping to sculpt the very galaxy it calls home, influencing how many stars are born and where they can form. In the far, far future, long after the last stars have flickered out, these dark giants may be the last large, coherent structures, slowly consuming the cold, diffuse remnants of their galactic domains. The question then becomes, what happens when these ultimate predators, having shaped their own galaxies, finally meet one another? The silent, invisible dance of black holes culminates in the most energetic event since the universe began its expansion. When two of these gravitational pits become locked in a mutual orbit, they begin a slow, fatal spiral, emitting ripples in the fabric of spacetime itself. These gravitational waves carry away energy, inevitably drawing the black holes closer together. In the final moments before their merger, they can whirl around each other hundreds of times each second, warping spacetime with unimaginable force before coalescing into a single, more massive object. Nobel laureate Kip Thorne, a pioneer in this field, described the detected signal not as a crash, but as the space-time warpage, the wobbling and ringing of the black holes, calling it a very clean system. The energy released in this last violent burst is staggering, briefly outshining the combined light of every star in the observable universe. Often, the newborn black hole is sent recoiling through space at tremendous speed, kicked by the lopsided blast of gravitational waves. These collisions, now routinely sensed by observatories like LIGO and Virgo, are more than just cosmic spectacles. They are pristine laboratories, allowing us to test Einstein's theory of general relativity under conditions of extreme gravity that are impossible to replicate on Earth. Each detection adds a new data point, helping us map the hidden population of black holes drifting unseen through the cosmos. How many of these dark remnants are circling each other in the void, waiting for their moment to collide? While these mergers release awesome power, their energy is utterly dwarfed by the final, catastrophic death of the universe's most massive stars. That brilliant flash is not the end of the story, but a violent beginning. For a few fleeting seconds, a gamma-ray burst can outshine every star in its entire host galaxy, releasing more energy than our Sun will over its entire 10 billion-year lifespan. These are the universe's most powerful explosions, and they announce the birth of the most extreme objects in existence. The late Dr. Neil Gehrels, a pioneer in observing these events, poetically called them the birth cries of black holes. There are two primary ways this cosmic scream is produced. The long bursts, lasting more than 2 seconds, are thought to be the final death rattle of a truly massive, rapidly spinning star as its core collapses directly into a black hole. The shorter bursts, lasting less than 2 seconds, are believed to be the catastrophic merger of two neutron stars, the incredibly dense corpses of dead suns. In both cases, the cataclysm focuses its unimaginable power into twin jets of radiation and particles, beams so concentrated they could be compared to a cosmic laser. If one of these jets were to be pointed directly at Earth from a nearby star, the consequences would be severe. The intense radiation could chemically alter our atmosphere, damaging the protective ozone layer that shields life from the sun's harmful ultraviolet rays. Such an event in our galactic neighborhood could potentially lead to a mass extinction, a reminder of how our existence is contingent on a relatively quiet cosmic environment. Yet, for all their local danger, these brilliant flashes are invaluable tools for science. They act as lighthouses, their light traveling across billions of light years, illuminating the vast stretches of gas and dust between galaxies. By studying the afterglow of a gamma-ray burst, astronomers can probe the composition of the distant universe and trace the history of star formation back to the cosmos's earliest epochs. What do these brief, brilliant deaths tell us about the violent conditions of the infant universe, where such explosions may have been commonplace? The remnants they leave behind are just as extraordinary as the bursts themselves, often condensing into objects of such density they defy all common sense. The death of the first generation of stars created the elements for worlds like our own, but their birth was an event of even grander and more violent proportions. In the pristine cosmos, mere millions of years after the Big Bang, the universe was a simpler place, composed almost entirely of hydrogen and helium. Without heavier elements to help clouds of gas cool and fragment, these primordial clouds could collapse into monsters. These were the hypothetical hyperstars, behemoths with masses reaching thousands of times that of our Sun. They would have blazed with ferocious intensity, burning through their nuclear fuel in a cosmic blink of only a few million years. Their lives were a spectacular, short-lived firestorm in the young universe. An even more exotic possibility is the quasi-star, a theoretical giant where a fledgling black hole formed at the very heart of a collapsing gas cloud. This object would be a hybrid engine powered simultaneously by the nuclear fusion in its outer layers and the voracious accretion of matter into its central black hole. As described by cosmologist Dr. Catherine Fries, the first stars were probably very massive, and their death seeded the universe with the first heavy elements. These colossal factories, if they existed, would have been instrumental in two profound cosmic processes. Their intense ultraviolet radiation would have begun the work of reionization, tearing electrons from atoms and making the universe transparent to light for the first time. More crucially, their cataclysmic deaths in supernova of unimaginable power forged and scattered the first heavy elements across space: carbon, oxygen, iron, the very building blocks of future planets and life. The black hole remnants from these explosions likely became the seeds that grew into the supermassive black holes we find at the center of galaxies today. How did the death of these first giants pave the way for the rich universe of elements we see today? Every atom of oxygen you breathe and every particle of iron in your blood was forged in the heart of a long-dead star, a legacy of that first violent cycle of cosmic creation. This enrichment of the cosmos set the stage for a new, more stable type of star to emerge, one capable of hosting planetary systems where the next great cosmic event could unfold. The stability of the universe might be an illusion, a temporary peace brokered by a delicate and perhaps accidental balance of quantum forces. Our reality depends on the precise mass of fundamental particles like the Higgs boson and the top quark. Current measurements suggest their values place the cosmos in a state of precarious equilibrium, a condition physicists call a metastable vacuum. Think of our universe not as resting in the bottom of a deep valley, but as balanced on a narrow plateau high on a mountainside. A gentle nudge, a random quantum fluctuation, could be enough to push it over the edge. Physicist Joseph Licken of Fermilab captured this unsettling idea, noting that the universe wants to be in a different state, so eventually it will get there. If such a fluctuation occurred, it would create a microscopic bubble of true vacuum, a region of space where the laws of physics are fundamentally different. This bubble would then expand at the speed of light in all directions, its wall rewriting reality as it moves. There is no force that could stop it, and no warning we could receive, as the wall itself travels at the ultimate speed limit. Inside this new region, the fundamental constants that govern how particles interact would be altered. The forces that bind atoms and allow for chemistry would likely cease to function, making the existence of matter, stars, planets, and life utterly impossible. This is not a risk that humanity can influence or accelerate. It is a property woven into the fabric of space itself. The probability of such an event occurring in our corner of the universe is vanishingly small on any human timescale, so small it offers no practical cause for concern. Yet its mere possibility as a fundamental existential risk forces a profound philosophical shift. It suggests that the laws of physics we take as permanent and universal might only be local bylaws, temporary arrangements in a much vaster and more exotic cosmic landscape. This quantum-level fragility stands in stark contrast to the slow, majestic evolution of galaxies, revealing a universe that is not only changing in its large-scale structures but potentially unstable at its very core. Even the universe's ultimate predators face a slow, inevitable decline. Stephen Hawking's brilliant insight revealed that black holes are not perfectly black. Due to strange quantum effects occurring right at the edge of their event horizons, they emit a faint whisper of radiation. This process, now known as Hawking radiation, acts like a slow leak, causing a black hole to gradually lose mass over time. Hawking himself noted the irony, suggesting that not only does God play dice with the universe, but sometimes throws them where we cannot see. For nearly all of a black hole's life, this evaporation is negligible. A black hole with the mass of our Sun would take far, far longer than the current age of the universe to evaporate appreciably. But in the profound stillness of the far future, this trickle becomes a torrent. As a black hole loses mass, it actually gets hotter, causing it to radiate energy away faster. This creates a runaway process. In its final moments, a stellar mass black hole could release the energy of 1 million hydrogen bombs in a hypothetical, brilliant flash. This ensures that in the timeline of the Big Freeze, black holes would be the last great structures to vanish. Their immense mass energy finally returned to the cosmos as a thin, cold sea of radiation. This elegant theory provides a profound link between the worlds of gravity, quantum mechanics, and thermodynamics, tying together the very large and the very small. What does it mean for the cosmos that even its darkest titans are temporary, destined to return their borrowed mass to the void? As these gravitational anchors fade, the particles they leave behind face their own strange destinies, governed by laws that are anything but certain. The apparent permanence of the world around us is a beautiful illusion. Every atom in your body, in the air you breathe, and in the ground beneath your feet is built around a core of protons, particles we have always assumed are stable forever. Yet this bedrock certainty of matter may have an expiration date. Many leading theories in physics, grand unified theories that seek to weave the fundamental forces into a single tapestry, suggest that protons are not immortal. The brilliant physicist Abdus Salam, who helped unify two of those forces, laid groundwork implying that over timescales that dwarf the current age of the universe, a proton could spontaneously decay into lighter, more fundamental particles. If this is true, then the fate of all atomic matter is sealed. Long after the last star has faded to black in the profound cold and darkness, the nuclei of every atom would slowly, inexorably disintegrate. The iron cores of dead stars, the rocky remnants of planets, even the diffuse atoms floating in the void would all ultimately turn into a faint mist of radiation and lightweight particles like positrons and neutrinos. This process, proton decay, would be the final erasure of the familiar universe. It would transform all normal matter, the stuff of worlds and life, into an inert, unstructured sea of energy. The ongoing, deeply sensitive experiments searching for this decay in vast underground tanks of water are not just looking for a rare event. They are conducting a direct test of our most profound theories about how the universe operates at its most fundamental level. What future could possibly exist in a cosmos where the very building blocks of reality have a finite shelf life? This dissolution of matter forces us to confront the stability of reality's very stage, the dimensions of space and time themselves. Our reality's very stage might be built on a temporary scaffold. The three dimensions of space and one of time we move through feel absolute, but some of our most advanced physical theories suggest this could be an illusion. According to concepts like string theory and brain cosmology, the universe we perceive may possess additional dimensions, curled up and hidden at scales far smaller than an atom. The stability of this intricate arrangement, however, is not guaranteed. A cosmic trigger, a shift in the underlying energy fields of reality, could initiate a catastrophic phase transition. Picture the universe not as a solid building, but as a delicate soap film. A sudden change in tension could cause that film to either pop or warp into an entirely new shape. In this case, the change would be to the number of dimensions themselves. The compactified dimensions could unfurl, or our familiar dimensions could suddenly collapse. As physicist Brian Greene explores in his book The Hidden Reality, the laws of physics are locked in a dance with the number of spatial dimensions. Everything from the strength of gravity to the nuclear forces that hold atoms together is precisely tuned for a four-dimensional world. If that number changed, the tuning would be instantly and violently shattered. In a region where a fifth macroscopic dimension opened, gravity might rapidly weaken, causing stars and planets to fly apart. Alternatively, if a dimension collapsed, gravity could become so intense that the entire universe would instantly crumple into a singularity. The very concept of atoms, of chemistry, of matter itself would become meaningless. This rewrite of physics would spread at the speed of light, a wall of fundamental law change leaving a completely alien and uninhabitable cosmos in its wake. While this scenario rests on the most speculative edges of theoretical physics, its implications are profound. It forces us to question the permanence of the most basic aspects of our existence. How would our understanding of cause and effect, of before and after, survive if the dimensionality of space itself was fluid? This possibility reveals that the greatest cosmic threats may not come from outside, but from a fundamental instability in the architecture of reality we take for granted. The quiet stability of our cosmic dimensions is a gift that might be revoked at any moment. This brings us to the 15th cosmic event, a collision of realities so profound it could reset the entire cosmos. Venture into the realm of string theory, where our familiar universe of three spatial dimensions is merely a three-dimensional membrane or brane, adrift within a higher dimensional expanse known as the bulk. In this mind-bending framework, our universe is not alone. Other branes, perhaps hosting their own parallel universes with entirely different physical laws, could be floating nearby in this hidden dimensional sea. Cosmologists Paul Steinhardt and Neil Turok have developed a compelling model where the Big Bang was not a singular beginning from nothing, but the result of a cataclysmic collision between our brane and another. They propose that the Big Bang is not the beginning of time but a bridge to a past filled with endlessly repeating cycles. In this cyclical model, the universe undergoes an endless sequence of expansion, cooling, and eventual renewal. The immense energy of a future brane collision would not just reshape our universe, it would completely reset it. This event would wipe the cosmic slate perfectly clean, erasing all structures from galaxies to atoms and flooding the newborn cosmos with a fresh, dense sea of matter and radiation, initiating a new expansion phase. This process could even explain the large-scale uniformity and geometric flatness we observe in our universe today, offering an elegant alternative to the theory of cosmic inflation. The entire epic history of our cosmos, from the first stars to the last black holes, would be just a single chapter in an infinite story of cosmic renewal, a concept of endless rebirth that stands in stark contrast to the finality of a heat death. Could every particle and force we know be merely the temporary echo of a collision that has happened countless times before? This vision of a cyclical cosmos challenges our deepest notions of beginning and end, suggesting that the universe itself may be immortal, forever dying and being reborn in a dance of branes across the hidden dimensions of reality. Stability is a fleeting state in the cosmos, a temporary pause in a relentless slide toward a final, unchangeable equilibrium. Deep within the cold, dark cinders of dead stars, a process so slow it defies human imagination is already underway. Over timescales that make the current age of the universe seem like a single tick of a clock, quantum mechanics allows for a strange kind of nuclear alchemy. In the intensely dense matter of white dwarfs and neutron stars, where atoms are pressed together until their electron shells merge, nuclei can still fuse. They do not overcome their mutual repulsion with heat and speed, but through a quantum trick known as tunneling, slipping through energy barriers as if they were ghosts. This is the realm of pycnonuclear reactions. The visionary physicist Freeman Dyson explored such far future physics, contemplating how matter would behave when given near infinite time. His theoretical work suggests that in a universe headed for a heat death, these slow, cold fusion processes would have one ultimate destination, iron 56. Iron is the most stable nucleus in the universe, the point where no more energy can be extracted by either fusing lighter elements or splitting heavier ones. One by one, over epochs of profound darkness, every remaining atomic nucleus in every cold stellar corpse would be transmuted. A white dwarf, the Earth-sized diamond remnant of a star like our Sun, would slowly crystallize into a perfect sphere of iron. A neutron star, a city-sized object more massive than the Sun, would undergo its own metamorphosis, its exotic matter ultimately yielding to the same iron fate. The final state of all baryonic matter in the cosmos would not be a diffuse gas, but a collection of cold, dark iron stars, or perhaps even a single, universe-spanning iron crystal. This is the ultimate victory of stability over change in the nuclear realm, the final, silent chapter of nuclear evolution. What would a universe composed entirely of iron mean for any potential for future complexity or life? It would be a cosmos where the periodic table has been rendered obsolete, where chemistry is impossible, and where the very concept of change has been extinguished. It is a metallic end state, a testament to the universe's relentless drive toward a permanent and unbreakable silence. The profound silence of an iron cosmos is not necessarily the final word. In a universe persisting for a near infinite duration, even the most wildly improbable events are not just possible, they are guaranteed to happen. This leads us to one of the most mind-bending concepts in all of cosmology, the idea of a quantum resurrection via Boltzmann brains. Named for the physicist Ludwig Boltzmann, this thought experiment pushes our understanding of probability and time to its absolute limit. In the unimaginable stillness of the heat death, random quantum fluctuations could, over an eternity, spontaneously assemble a fully formed, conscious mind, complete with a complete set of false memories. This entity, a Boltzmann brain, would believe it had a past, a body, and a world, when in reality it was just a momentary, random tick in the void. Philosopher Dr. Sean Carroll highlights the stark implication, suggesting that if the universe lasts forever, then any structure that can possibly fluctuate into existence will do so an infinite number of times. The truly unsettling part is the statistics. In an eternal cosmos, it is actually far more probable for a single, isolated consciousness to randomly appear than for an entire ordered universe like our own to re-emerge from the chaos. This presents a profound philosophical puzzle. How can we be sure that we are not such random fluctuations ourselves, momentarily dreaming up a vast cosmic history that never truly occurred? This is not a call for existential dread, but an invitation to contemplate the very nature of observation and reality. It forces us to recognize that our current cosmological models may have deep, unresolved paradoxes when stretched across infinite time. Are we the products of a coherent 13.8 billion year narrative, or are we the most recent fleeting thought in an endless, silent eternity? This bizarre possibility challenges the foundation of what it means to be real in a cosmos without end. Our own experiments could, in theory, become the trigger for the universe's final rewrite. This is the unsettling possibility of a false vacuum collapse initiated not by random chance, but within a particle accelerator. When scientists at facilities like the Large Hadron Collider smash particles together at nearly the speed of light, they recreate energy conditions not seen since the universe's first moments. The speculative fear is that such a concentrated burst could create a microscopic bubble of that true, lower energy vacuum, a bubble that would then expand at light speed and erase the laws of physics as we know them. This concern was taken seriously enough that top physicists conducted extensive safety reviews. Their conclusion was one of profound reassurance. Nature itself has been running far more powerful experiments on Earth for billions of years. Cosmic rays, particles from deep space, routinely strike our atmosphere with energies vastly exceeding anything we can produce in our machines. As former CERN Director General Professor Rolf Dieter-Heuer noted, nature has already conducted the equivalent of about 100,000 LHC experimental programs on Earth, and the planet still exists. The fact that the cosmos remains intact with its laws stable is the strongest possible evidence that our experiments pose no threat. Yet the very act of contemplating this risk forces a deep philosophical reckoning. It places a unique responsibility on our species, framing humanity not just as passive observers of the cosmos, but as active participants who must weigh the immense benefits of knowledge against risks that are remote yet ultimate in scale. How do we balance the undeniable drive to understand our universe's foundation with the ghost of a possibility that our probing could one day change it forever? This is a question that brings the vast, impersonal forces of cosmic change directly into our own laboratories, reminding us that the future of reality is not just about what the universe will do to us, but what we, with care and wisdom, choose to learn about it. The vastness of space might not be empty, but seeded with artifacts from intelligences we cannot yet comprehend. This speculative threat moves beyond natural cosmic disasters into the realm of deliberate or accidental design. A civilization that has mastered interstellar travel could theoretically construct a relativistic kill vehicle, an object as simple as a dense rock accelerated to a significant fraction of light speed. At such velocities, its kinetic energy becomes apocalyptic. The impact would not be a mere explosion. It would be a planet-shattering event, releasing energy on par with a stellar detonation and sterilizing an entire world in an instant. Alternatively, the danger might not come from malice but from indifference. A dormant alien probe, perhaps a self-replicating von Neumann machine designed to harvest resources, could misinterpret our solar system as raw material. Upon activation, it might begin a process of disassembling planets to build copies of itself, an unstoppable chain reaction that consumes entire stellar systems. Astronomer and author Dr. David Brin has written extensively on such existential risks, suggesting that our greatest future challenges may be sociological, born from encounters with technologies far beyond our own. While this sounds like science fiction, it serves a profound philosophical purpose. It forces us to recognize that intelligence itself can become a cosmic force, a power capable of reshaping star systems through intent or catastrophic accident. This shifts our perspective on humanity's own future. If we survive long enough to travel between the stars, could we be the ones to wield such terrifying power? And what ethical frameworks, what deep wisdom would we need to develop to ensure it is never used? The capacity for intelligence to influence cosmic evolution compels us to look upward, to the very largest structures that intelligence might one day seek to command. These vast cosmic continents are the final expression of gravity's ambition. On the largest scales we can map, galaxies are not scattered randomly, but are gathered into immense clusters, which themselves are drawn together into sprawling superclusters, the largest gravitationally bound structures in the entire universe. Our own cosmic address places us within the Laniakea supercluster, a breathtaking filamentary web of 100,000 galaxies spanning over 500 million light-years. Astronomer R. Brent Tully, who led the team that defined Laniakea, fittingly calls it our home supercluster, a continent in the cosmos. Its formation is a story written in dark matter. The invisible gravitational scaffolding of the cosmos pulls ordinary matter into these colossal patterns over billions of years, a slow, relentless accumulation of mass. But this grand construction project is locked in a cosmic tug-of-war. The same dark energy that accelerates the universe's expansion is working against gravity's pull, trying to stretch these vast structures apart. The future of superclusters like Laniakea depends entirely on the outcome of this struggle. If dark energy's influence were to weaken or even reverse in the far future, gravity could finally win. These superclusters would continue to merge, coalescing into a single, universe-spanning hypercluster, a final, immense island in the void. Conversely, if dark energy continues its accelerating push, these great cosmic continents will be the last great structures to be disassembled, their gravitational bonds finally overwhelmed by the stretching of space itself. By carefully mapping the motions of galaxies within Laniakea and other superclusters, astronomers are essentially taking the universe's vital signs. The subtle pull and push on these galaxies reveals the balance of power between the dark forces of gravity and expansion. How does the mapping of these vast structures help us predict the universe's final configuration? It provides our clearest view of the battlefield where the ultimate fate of the cosmos will be decided. This grand architecture, built over eons, is now testing the limits of gravity itself, a force we once thought absolute but is now revealed to be a local power in a dark energy-dominated realm. The invisible skeleton of our cosmos might not be as permanent as we believe. Dark matter, that mysterious substance accounting for roughly 27% of everything in the universe, is the hidden architect of the cosmic web. We have always assumed it to be a cold, passive substance, ghostly particles that only feel the pull of gravity. This stability is a foundational pillar of modern cosmology, the reason galaxies can form and hold their shape. Yet what if this cornerstone itself could crumble? Theoretical physicists like Dr. Lisa Randall have proposed models where dark matter is not simple, but possesses a rich and complex particle physics of its own. In such a framework, dark matter could be susceptible to a dramatic phase transition. Much like water abruptly turning to ice, the entire dark matter content of the universe could suddenly shift its state or properties. This would not be a quiet change. If dark matter were to become strongly self-interacting, its particles could begin to bounce off one another, fundamentally altering how it clumps under gravity. The delicate balance that allowed galaxies like our Milky Way to form and spin without flying apart would be shattered. Vast halos of dark matter, the gravitational anchors for every galaxy, could either collapse inward or evaporate outward in a cosmic reconfiguration. Such an event could trigger a second wave of chaotic structure formation, or it could do the opposite, causing the majestic spirals and ellipses we see today to simply dissolve, their stars scattering into the void. The entire distribution of mass across the universe would be rewritten. While there is no current observational evidence for this, the possibility forces a humbling realization. Our entire understanding of the cosmos is built upon the assumed behavior of something we cannot see. How much of the universe's grand story is dependent on the continued, silent cooperation of this dark foundation? This potential for change hidden within the dark sector finds a parallel in the ultimate fate of the universe's most enduring structures. The same quantum fields that sculpted our newborn universe might one day awaken again. The prevailing theory of cosmic inflation suggests that a fraction of a second after its birth, the universe underwent a fantastically rapid exponential expansion, smoothing it out and planting the seeds for all future galaxies. This process was likely driven by a scalar field known as the inflaton. But what if this was not a one-time event? Cosmologist Dr. Alan Guth, who first proposed inflation, developed the concept of eternal inflation, where the process stops in some regions, creating bubble universes like our own, while continuing unabated in the space between them. This paints a picture of a grand, eternally inflating meta-universe, a frothing sea of reality where new cosmic domains are constantly being born. Within this framework, a future phase transition in a fundamental field could trigger a second, localized inflationary epoch right here in our cosmic neighborhood. The trigger could be a random quantum fluctuation or a gradual change in energy, flipping the field into a high-energy state. The moment this new inflation began, it would be a point of no return. Space itself would begin stretching at an incomprehensible rate, far faster than the speed of light. Every structure we know and see, every galaxy, every star, even the very atoms that make up our local group, would be pushed apart with such violence that they would effectively vanish from each other's view. The cosmic horizon, the distance within which objects can ever interact, would shrink to nearly zero, isolating every particle in a sudden and profound solitude. This new inflation would take a tiny, perhaps microscopic, patch of our old universe and blow it up into a new, vast, and perfectly flat cosmos, erasing all traces of the previous one. It would be the ultimate cosmic reset button, wiping the slate of history completely clean and initiating a brand new timeline. This new universe could even emerge with slightly different fundamental constants, altering the strength of gravity or the nuclear forces, making the formation of stars and life either easier or impossible. Are we living in just one bubble among an infinite number in an eternally inflating meta-universe? This staggering idea challenges the very core of our cosmic story, suggesting that our universe's entire history is not a singular, linear narrative, but merely one temporary arrangement in an endless cycle of creation and rebirth. The fabric of spacetime might be scarred by relics from its most violent infancy. These scars are known as cosmic strings, hypothetical flaws in reality's structure that could be thinner than a proton yet denser than a mountain range. They are not made of atoms or energy as we understand them, but are thought to be one-dimensional cracks that formed as the fundamental forces of the universe froze into their current separate states, a process akin to the way ice crystallizes and forms fissures in water. If such an entity exists, its gravitational influence would be immense, warping the space around it like an invisible, infinitely long wire cutting through the cosmos. The pioneering work of physicist Alexander Vilenkin highlights the profound significance these objects would hold, suggesting their observation would be a landmark scientific event. A cosmic string drifting through our solar system would not rip planets apart, but its subtle gravitational tug could nudge them into new, slightly altered orbits over vast timescales. The most telling sign of its passage would be in the light from the distant universe. Astronomers might see the same galaxy appearing twice in the sky, its light split and bent around the string's immense gravitational field, or detect a sudden, sharp discontinuity in the ancient glow of the cosmic microwave background. Finding one of these primordial filaments would be like uncovering a fossil from the universe's first moments, offering direct evidence for the grand unified theories that attempt to describe how all forces were once one. What secrets about the cosmos' explosive origin are locked within the geometry of these spacetime cracks? Their hypothetical existence is a powerful reminder that the largest structures we see today were seeded by imperfections written into reality at the very beginning. This final stellar flame will not be a brilliant giant, but a slow, patient ember. Trillions of years into the future, the last star to ever form will ignite within a galaxy that has long since merged with all its neighbors. The raw material for this final act of creation will be the cosmic dust left over from countless stellar generations, a gas so enriched with heavy elements that it can only coalesce into the smallest, most frugal of stars. This will be a red dwarf, a star so tiny and dim it might glow with only a faint, ruddy light, yet its potential lifespan is almost beyond comprehension. Astronomer Dr. Fred Adams, in his work describing the universe's 5 ages, labels this vast stretch of time the degenerate era, a period defined not by vibrant birth but by the slow, steady burning of these last remaining stars. The universe will be a much darker place, its grand spiral galaxies having faded or merged into bland, elliptical shapes, with the brilliant blue giants and sun-like stars a distant, extinct memory. This final red dwarf will be the universe's last source of light, not born from sheer gravitational collapse or the faint heat of cooling stellar corpses. For trillions of years it will burn, a solitary beacon in an ever-cooling cosmos, until the day comes when even its immense reservoir of hydrogen is finally depleted. It will then slowly dim, cooling from a red ember to a black, cold cinder, a black dwarf. That quiet moment, the cooling of the last stellar ember, marks the definitive close of the stelliferous era, the age of stars that defined our cosmos from its infancy. It is a profound transition, the moment the universe's primary engines of light and energy fall permanently silent. What does it mean for a cosmos to continue for an almost infinite future, now devoid of the very processes that built the elements of planets and life? The long, dark age that follows will be a universe running on the last of its battery power, a gradual fading into a cold and permanent night. Our reality could rewrite itself in a single, silent moment. This final event is the ultimate expression of quantum theory, where the entire cosmos, trapped in its current state of false stability, tunnels as a whole into a new existence. There would be no expanding bubble of destruction racing at light speed. Instead, every point in space would undergo the same instantaneous transition, a coordinated flip of a cosmic switch. The laws of physics that govern everything from the orbit of an electron to the pull of a black hole would be replaced in an instant. The universe we know would not be destroyed by fire or ice, but simply overwritten, its fundamental code replaced with a new set of rules. This new reality might have more dimensions or fewer. Gravity could be 1 billion times stronger, instantly crushing all structure, or so weak that matter simply evaporates into a formless mist. The concept of a star, a planet, or an atom would become meaningless relics of a previous configuration. This is not a death, but a spontaneous and total rebirth, a reboot of existence itself. The probability of such a universal quantum jump is so infinitesimally small that it is practically zero within any conceivable time frame. Yet, the mathematics of quantum field theory do not explicitly forbid it, pushing our understanding of reality to its absolute limit. This final cosmic event presents the most profound question of all. Are the physical laws we have dedicated centuries to understanding merely local bylaws, a temporary arrangement in an infinite landscape of possible realities? Our entire cosmic story, from the first star to the last thought, might be just one possible verse in an endless poem of creation. From the intimate fate of our own sun to the abstract possibility of a quantum reboot, these 25 cosmic events form a single, interconnected story. They are not isolated catastrophes, but threads in a grand tapestry of change, woven by the same fundamental forces. The explosive death of a massive star does not merely end one story. It seeds the cosmos with the heavy elements required for new planets and potentially new life. Those same stellar corpses can collapse into black holes, whose eventual mergers send ripples through the fabric of spacetime, a gravitational echo of their violent creation. On the largest scales, the magnificent cosmic web, sculpted by the invisible hand of dark matter, is locked in a slow-motion duel with the repulsive push of dark energy, a struggle that will determine the universe's ultimate architecture. This grand synthesis reveals a crucial truth: our present stelliferous era, this age of brilliant stars and active galaxies, is merely a single, vibrant chapter. It is a temporary flourishing of light and complexity, bookended by vastly longer epochs of darkness and simplicity. To comprehend these potential futures is to do more than simply satisfy a scientific curiosity. It frames our own fleeting existence against a backdrop of almost unimaginable time and power, casting the phenomenon of life as something both incredibly fragile and profoundly precious. How do we find meaning when our entire history is but a spark in a cosmic night that will last for trillions of years? This holistic view of a cosmos in perpetual transformation invites a final, deeply personal reflection on our own small, yet significant, place within its unfolding story. From the predictable expansion of our sun to the speculative decay of the vacuum, these 25 cosmic events paint a portrait of a universe in constant, dramatic flux. We have seen that change is the only constant, operating on scales both imaginable and utterly beyond human comprehension. This grand narrative reveals a cosmos where creation and destruction are two sides of the same coin, where the death of a star seeds the birth of a planet, and where the same force that builds a galaxy may one day tear it all apart. The poet Robinson Jeffers wrote, "The greatest beauty is organic wholeness, the wholeness of life and things, the divine beauty of the universe. Love that, not man apart from that." His words are a profound reminder to find our awe in the entire cosmic process, not just our fleeting part within it, to marvel not only at the spark of life, but at the silent, cold eternity of iron stars, and to see the same fundamental beauty in the fiery birth of a nebula as in the quiet evaporation of a black hole. Let this exploration be a humbling reminder of the sheer grandeur of the cosmos, and a call to continue looking up and questioning the heavens. The universe's story is still being written, and each new observation, each flicker of data from a distant telescope, adds a new word to its epic. We encourage you to share which of these cosmic events you find most fascinating or terrifying in the comments below, and to subscribe for more journeys to the edge of understanding. The cosmos remains full of mysteries waiting for their moment to be uncovered.